Hi everyone, this is just a quick solution video for, I guess we called it the week 1 challenge, but the Haversine function to calculate the distances between two locations given their latitude and longitude. So just on a sphere is the greatest way to say that. So we have to start off, of course, by importing math and for the function that we're comparing against, importing Haversine. So have all this up here, just bring in those libraries, that code that these people who know Python a lot better than we do have written already, that we can just use for our own purposes. And then here we go, just stating that location and storing it within a tuple. I don't know within you're learning Python if you talk much about tuples, but it's an immutable data type. If you can look that up if you don't know what that means. And we're just storing Lincoln's location in one and the y-school in another, mainly for the use here. So we're going to step through a few things that are important to do, and you might miss some of these out, and so you might have to jump around in the videos to make sure that you catch everything. So of course we have our example. My bad, my alarm just went off to remind me to do something. But if we have the results distance here that we're going to print out, as you know, we have to multiply 2 by the radius of the Earth, and in this case, once it updates there, I believe that's in miles. So the Earth's radius, is 3,950 miles approximately, and then we can do the rest of the math. So the first outer loop we need to do here over everything is to take the arcsine, which arcsine, asine, we call using this math.asine, and then within that, of course, if you're looking at the right page here, there's the square root. So we're going to take the square root of all that. So we take the square root of all that, and now we'll take a look at this next little bit here. So we'll work our way from the outside in. If you guys have that Wikipedia page open that has that little description, that would probably be helpful at this point if you haven't been able to figure it out yet. But starting at the outside, we're going to use the star operator, which is to the power of. So that is squared. That's what that is. So taking a step in, then everything is divided by 2. So we made sure and placed that, or my bad, actually, you're taking the sign of what's inside of this right here. So our next function or operation that we have is math.sine, which of course is sine. And we take lat2 minus lat1 and divide that by 2. So that's that first chunk there. Now there's some addition here, and we need to be very careful with parentheses, just of how how complicated and a little weird this function is. And then we're going to add the cosine of lat1. That's relatively easy. And then multiply the cosine of lat2. We technically don't need parentheses here. Between all of this stuff right here, it wouldn't be a bad move, but we do technically not need them. It always helps to have more parentheses than this, though. Yeah, like I said, multiplying the cosine of latitude 2, and then we're going to have a very similar, grouping of things like the first one we talked about. So on the outside, we're taking the second power squared, right? And then we're going to take the sine of the junk in the middle here. So long 2 minus long 1. Longitude 2 minus longitude 1. Divide that by 2. And then we're going to take the sine and then square it. Of course. It all kind of just fits in here. It's really hard to think about as one big thing in total. But if you take this problem and break it down into chunks, starting from the biggest piece outside, we have this multiplied by 2 and then 3,950 and then some other junk. Now we can start breaking down the other junk by taking the arc sign, the square root, and working on those individual parts. So the other thing you need to be aware of when doing this project is this right here doesn't work using the latitude and longitude we provided. Now, saying that, I don't know if you have heard of radians. I'm sure some of you have and some of you haven't, but it's another way to approximate a circle. So, a typical circle has 360 degrees in it, or not typical, every single circle has 360 degrees in it. And that in radians is 2 pi. So it's really weird to think about, but basically, if you put your hand on one side of the circle and go all the way around, your hand goes through 360 degrees. And if you do that same motion, slowly you're going to add up from pi halves, pi, 3 pi halves, to 2 pi, and if you make your way all the way around that circle. And I'll see if I can come up with a really quick example of that through Google. So radians to degrees, I'm going to go to images here. So, yeah, well, this is a hint. 1 degree is equal to pi over 180, that's our conversion factor here. But yeah, here, so like we said here, 360 degrees, also 0 degrees is 0 pi, 30 degrees is pi over 6, 45 pi over 4, and we can find all these using that conversion factor that we'll show in just a second. So the conversion factor is pi divided by 180, like pi 3.14 divided by 180. You could use a decimal there, but it's more accurate, of course, to use that entire calculate it on the fly or whatever. And then we're just going to take lat 1, exactly what we say it is up here, and then reassign it with the conversion factor. So just converting them from degrees to radians. I know for some of you that's probably a really weird thing to think about, but it's something that hopefully you'll learn about in higher math and maybe even further throughout this project. So you can also go in and change these like we said. I'd be really excited to see some of the locations, and if anyone tried to accomplish this with a slightly different method, which is possible. Yeah, thank you guys for listening. If you have any suggestions, we definitely are willing to change in order to make something work better for you guys. So thank you very much. Have a good holiday.